Okay, welcome. We are talking about periodic trends. You are going to definitely need table S for this one, so make sure you have that available. So the first thing is, what is atomic size? Atomic size is also known as radius. So atomic size is the size of an atom measured in atomic radius, or picometers are the exact units. So if you were to look on reference table S, you see the rightmost column is atomic radius. So PM is picometers, and pico, if you flip to the front, pico is 10 to the minus 12th of a meter. So picometer. There we go. So let us figure out. Now remember, the genius of Mendeleev is that he figured out that the periodic table not only shared increasing atomic number as you went across a period, but there were physical and chemical properties that had periodic repetitions, and one of them was atomic size. So again, we're looking at atomic radius here. The goal is to figure out what happens to atomic size as you go across the period. So again, this is radius, atomic radius. So if I have my periodic table here, oh my gosh, that's not good. Yikes. And we're going across a period. So here's my goal. You choose one element here, find the atomic radius. Now we're going to ignore group 18 because group 18, you know, is special. Then choose another one on this side and see what happens. Sure, we could figure out every atomic radius in between, but there's going to be some fluctuation. So we're going to see if we've gone up or gone down. So I'm going to look at, let's see, how about potassium and all the way on the other end, but not noble gas. Let's look at Br. So let's look at atomic radius for potassium. That is 200 picometers. And bromine, where are you? 117. So what happened to the atomic radius? It decreased. So I can actually, I think I can. Can I get rid of? Oh, sorry. I guess I don't know how to erase. Okay, let's look at groups. So I'll try to draw here so you don't get confused. So again, we're not going to look at group 18. So I'm going to look at somebody towards the top of the group and at the bottom of the group. So how about I look at, let's see, how about lithium to francium? So lithium has an atomic radius of 130, and francium, way at the bottom, has an atomic radius of 242 picometers, which means it's an increase. Oops. So you don't ever have to memorize these. And again, I'm sorry I wrote over there. As long as you know how to determine it every time. And of course, you know, this is a general decrease across a period. Maybe it'll go down and then maybe it'll up and so there could be some fluctuations. We could graph it and you'd see that sometimes there are some differences, but in general, it's a decrease and an increase. I removed this from the notes, but this is just kind of a silly thing you can remember. And it only has to do with atomic radius. Atomic size increases as you go down a group, like the snowman shape, because there are more energy levels. Okay, so snowman, you build it like this, right? But atomic size decreases as you go across a period, like if you tipped him over. So it's like, you know, shove him in this way and woo. This is because there's greater attraction between the nucleus and the increasing number of valence electrons. So the positives and the negatives, there are more of them, and so they kind of squish them closer. Again, this isn't anything you need to write down in your notes. Okay, the next thing we're going to talk about is ionization energy. Ionization energy, so find that on table S. Ionization energy it's known as first ionization energy. That's okay. It is the first column of data after the name. Okay, so I guess we should probably talk about what it means. Ionization and energy. So the energy required to remove an electron from an atom. So how much energy does it take to take energy does it require to take electrons away? Some atoms really want to lose electrons and some don't. So that's important to know first. If you have a high ionization energy, it's going to require a lot of energy to remove the electrons. So if you take a look at nonmetals, which you should know are on the right side of the periodic table, those are going to have higher ionization energies. And if you notice, it's because they have negative oxidation states, which we haven't talked about too much just yet. But if you have a negative charge, that means you've gained electrons, right? So if you've gained electrons, and that's what you like to do when you form ions, you're not going to want to give them away. So it's going to take a lot of energy to remove electrons, okay? It's kind of like I'm going to go into your house and I'm going to steal your phone and some, your diamonds and money. Those are valuable to you. You're not going to give them up easily. You'll put up a fight. However, if I go to the curb and I steal your garbage, you're going to say, have a great day. Enjoy that. I don't care for that. It has no value to me. That's kind of like what metals deal with. Because if you look on the periodic table, by the way, they are the left side, they have positive oxidation states. And remember what that means. Oxidation states that are positive means those elements like to lose electrons. So if I like to lose electrons, I'm not going to put up much of a fight when you want to take them from me. So that's why they have lower ionization energies. So it's like if you have a high ionization, it's going to be you're stealing cash money versus stealing trash. Yeah. So if you don't remember that, let's just take a look. Let's do what we did before. Let's take our periodic table. Let's look at potassium and let's look at bromine. So potassium has an ionization energy of 419 kilojoules per mole. So again, energy. We haven't talked about moles. That's okay. Bromine has an ionization energy of, 1140 kilojoules per mole. That's a much, much greater increase. So across the period, ionization energy increases. So if we were going to look at the group, oh my gosh, the worst periodic table ever. Let's look at lithium and francium. So lithium has an ionization energy of 520, and then francium is 393. So that's a decrease. So maybe you've noticed that if it increases one way, it's going to decrease the other, and vice versa. But you don't have to memorize this, folks, because you just have to look it up. Periodic table, or table S, excuse me. Having the same general idea of electrons, okay, stealing electrons, we have something called electronegativity. Electronegativity is like the middle column of table S. Notice that there are no units for electronegativity. Electronegativity is basically how strongly an atom is pulling for electrons in a chemical bond. I like to think of it as greediness for electrons. You can attribute electronegativity to the scientist Linus Pauling. And he was doing all kinds of experimentation with elements, and he's trying to figure out, okay, and he knows that certain elements are more greedy for electrons than others. And so he's like, all right, I'm going to say that, fluorine, super greedy for electrons. And I know that others are less. So I'm going to give fluorine a value. And it doesn't have any units. It's just kind of a value. And it could be any number I want. And I'm going to choose 4. 4 means nothing. This is an arbitrary scale. Arbitrary. So the numbers don't mean a darn thing, but you can tell by looking at them who's greater than, who's less than, okay? So again, it's greediness for electron. Fluorine is the greediest on the periodic table. It really wants electrons, okay? Because it's got the largest value of 4. And it's 4, that's it. There's no units. So if you notice elements close to fluorine, like chlorine, sulfur, oxygen, that kind of stuff, they have high electronegativity. So let's see, chlorine is a 3.2, oxygen 3.4, nitrogen 3. You know, they're up there. They're in the 3s. But things that don't want electrons, remember, the metals, they want to get rid of them anyway. So I'm not going to be greedy for something I don't want. So they're going to have a low ionization energy. So if you look at things like, I just happen to look at barium, it's a 0.9. Sodium, 0.9 also. Potassium, 0.8. So they're much, much lower. So again, let's take a look. All right. Let's look at our two friends. And I'm only choosing these because they're on opposite sides of the periodic table. You could choose any elements on either side. Again, I would ignore group 18 just because they're a little bit different, especially in terms of electronegativity. So potassium has an electronegativity, where are you? You're hiding. 0.8. And remember, there's no units to that. And bromine has an electronegativity, where is bromine? 3. So what happened as you went across a period? It increased. And maybe you remember that if it increases one way, it's going to decrease the other. Or you could just look. Let's just look at the periodic table. We don't need to memorize a darn thing. Let's look at lithium because it's at the top. Let's look at francium because it's at the bottom. Lithium has a value of 1.0, no units. Francium has a value of 0.7. Although it's not a large decrease, it is indeed a decrease. Okay? Let's talk about why noble gases don't have any electronegativities. Notice that they have a dash, like krypton is a dash, helium's a dash, chlorine's a dash. Why would they have a no value? Because they don't want electrons. They don't want electrons. They don't want them at all. They have the stable electron configuration as is. Remember, they have that full outer shell. So that's why they don't have any need for electrons. So they're not greedy at all. They're like, yeah, no big deal. Doesn't apply to me. Finally, let's talk about ions. So the periodic trends of ions. So again, recap. If you remember, cations are positive. And let me embarrass myself a bit. Positive cations. Anions are negatively charged. Positive. Okay, so if you are a cation and you're losing electrons, when you lose weight, what happens to your size? Your size is smaller, much like happens when you lose electrons. When atoms are losing their electrons and become cations, their atomic size decreased. And I know that my college prep non-regions didn't talk about electron configurations in this way, and that's fine. You could also talk about it. Let's see, sodium. What is sodium? Sodium is 2-8-1. So 3 energy levels. When you lose that last electron, you're just 2-8. So look, there's a whole extra energy level that is gone when you become a cation. So when you lose electrons, your size gets smaller. And actually, it's not really atomic size. It would be called ionic size. Anions, think about it. You're gaining electrons. When you gain weight, your size increases. So again, this is of the advanced electron configuration. We could talk about fluorine is 2-7. Now, although we didn't go up an energy level, we gained another electron, making it larger. Very insignificantly larger, but still larger all the same. Very briefly, metallic versus non-metallic character. You should know where those regions of the periodic table are. So where the metals are, where the non-metals are. The elements near the left are more metallic, while those near the right are more non-metallic, and that should make sense because on our periodic table, which is getting messier by the moment, here's our zigzag. These are metals, these are non-metals. So if you travel this way, you're becoming less and less metallic. And the opposite is true for groups. For any group, the elements near the top are going to be more non-metallic, like up here, versus down here. So the most metallic is the lower left corner, francium. Most non-metallic is the upper right, except for the noble, so probably fluorine. Yeah, so there's that. Just kind of bringing it into a picture for you. Finally, activity of elements, how willing an element is to react. That's activity. So the most active metals are the lower left corner. Most active nonmetals are the upper right. They're like the extremes there. The most active elements form the most stable compounds. Because if you really want to lose electrons, and somebody really wants to gain electrons, and they come together and make a compound, super duper stable. Everybody's happy. Okay? I believe oh, nope. One last thing. Allotropes. Allotropes. So what an allotrope is one or two more different forms of an element in the same phase, but they have different physical properties. Classic example, carbon. Carbon has 3 allotropes. We've got our very familiar graphite, okay, pencil lead. Never say pencil lead again, it's graphite. This is what it looks like on a molecular level. These are sheets. They're just sheets. And when you write with a pencil, you're leaving a trail of carbon atoms behind. And so that's why it breaks so easily, because they just shred off in sheets. Ooh, diamonds. The hardest on Mohs hardness scale. Look at how the molecules are arranged differently. So look at how they're interconnected. We'll talk later about how they're called network solids. So they're much, much stronger than these loose sheets. And then perhaps you're not familiar with this one. This is called a Buckminster fullerene. Sometimes it's also known as a buckyball. And it looks like a soccer ball, see? But these circles are all carbon atoms. And these represent the bonds. And it's C60. So carbon can form 3 different, totally different physical properties, but they're still just all created of carbon. There's nothing else. It's just carbon. Another one would be oxygen. Would be oxygen and ozone. So oxygen is O2, ozone is O3, and I don't have pictures of them. They are gases, but notice that they have much different physical properties. So another example of allotropes. This one's maybe easier because you can see them. All right, thanks for watching. If you have any questions, please reach out. Take care.